You may have seen my last YouTube short videos about the upcoming nova T Corona Borealis, and it will be visible to the naked eye since it will be kind of bright. But what really is brightness in astronomy? Hey everybody, and welcome to another episode of Compressed Cosmos here on my channel Astronomy. Now, I already mentioned it in the introduction. We are going to talk about brightness in astronomy. And this is due to the reason that I was making two short videos about the nova T Corona Borealis. And it's somewhere in the crown, so just go to my videos, or if you look here in this short animation, you see the constellation Corona Borealis, and here in this spot we have a star which is kind of faint. It has currently a brightness of around 10 magnitudes, and it will increase its brightness to around 2 or 2.5 magnitudes. But well, what really is brightness in astronomy? Now I'm asking this question now a third time, and I think without further ado, we are going to dive directly into a short Python code to really see what is it all about and to put things a little bit into perspective. And maybe you will be also kind of surprised how sensitive our eyes are, and it's pretty crazy that we even see the stars at all. So let's switch to the coding. Well, and as always, today's code is stored in my GitHub repository Astronomy YouTube tutorials, and then in the folder Compressed Cosmos with the file compressed cosmos brightness.ipynb. And here we have a short small batch. We simply click on Open in Colab, and then we have the corresponding code here. Now, first of all, we are importing a math function. A short warning is coming. You can trust the code. Yeah, you see the code, so you can trust me. But first we need to connect to some server, and then we have the math module imported. Now, the thing is now, what I would like to do first is to compute like the relative brightness between two values. Like, as I said, T Corona Borealis will have a value of 10 magnitudes, or it has it now 10 mag, and it will increase to around 2 mag. Now, what does it really mean? Yeah, I wrote also here in a comment. What is it? Is it like a factor of 8 or so? What is it all about? Well, the function is a logarithmic function basically. So we have here the lambda function, which I simply call the delta mag, and we have here 10 to the power of 0.4 times delta magnitude. So the delta between the one value and the other value. Now the question is, why is there like some 10 to the power of something something? Why does it smell like logarithm also here? Well, this is a little bit based also on the very historical definition of this star's brightness. And this is because of, well, let's switch to some images of this guy called Hipparchus. Now, Hipparchus was a Greek astronomer who classified the stars the first time by their brightness and said, okay, you know what? The faintest stars we see with the naked eye, they have the value 6, and the brightest one have the value 1. Now, it's a very human-driven approach without any instrument or something like that, but well, it worked out somehow, and we are still using this definition until today. But yeah, the brightest star for us now, or the reference, is Vega with a value of 0. And there are also way fainter stars and also brighter ones like the sun, for example. But yeah, let's keep it like this first. We consider this definition, and we work here now with the delta value. And the delta value here, I mean, this is a little bit overkill, but if you want to replace values, you can simply change the numbers here. The delta is of course 8. And if we put the value 8 in our function, let's see what's happening. What does it say? Well, that our nova of T Corona Borealis will be brighter by a factor of around 1,500 compared to now. So that's pretty bright, I would say. It's very, very bright. And if you consider even other events that were maybe not visible to the human eye, but maybe to some instruments, there are events that are even way brighter compared to the, let's say, original karma state. But that's pretty much a number 1,500. Now the question though is, what does it mean, like a magnitude, right? It's like one astronomical union is one astronomical unit is around the distance between the sun and the earth. It's around 150 million kilometers. But what is 1 mag or 2 mag? How does it translate to something more human readable? And for this, we are considering some paper from the International Astronomical Union. I put the link here also as a comment. And there we have like the value for the 0 mag irradiance level. Now the irradiance level is like how many watt per square meters we have. And we need some kind of reference number, the 0 number, which is basically Vega, which has a magnitude of 0. But it's also half the truth because there are like different wavelength bands that you can consider. So you can, for example, compute the brightness of a star in the so-called bolometric magnitude, which means it's like the complete brightness from, let's say not only the visible light, but also the ultraviolet and infrared and what have you. But you can also consider shorter bands, like let's say, especially in the red light or in the infrared and so on, and then compute different magnitudes and different irradiance levels for different bandwidths, which is interesting because some stars, let's say, are a little bit brighter in the bluish spectrum or in the redder and vice versa. So it's always important to know to what color filter the magnitude is referring to. Now the irradiance here is also a small lambda function where we use the apparent magnitude, and we have here 10 to the power of minus 0.4 times the apparent magnitude plus the 10th logarithm of the 0 point reference. Let's call it like this. Yeah, here in this case it's the bolometric magnitude. Now if we compute here the value for our nova irradiance, our magnitude of around 2, we get the result in watt per square meters. And the magnitude of 2 we know from Hipparchus, it will be visible. Magnitude of 2 is easily visible to the naked eye. Maybe not in the inner city of New York or so because it's a little bit too bright, but in some rural areas it's easily visible. And now it's getting interesting how many watt per square meters are hitting Earth. And we execute the code and we see it's around 4 times 10 to the power of minus 9 watt per square meter. And these are insane values because imagine the broad daylight where the sun is shining, you know, you live your daily life, you see everything, of course. There we have in average, let's say, round about 1000 watt per square meters. And in the night, you see the stars, right? You see the small dots in the sky, and they have an irradiance level that is orders of magnitude smaller. And of course, you can say, yeah, simple. These are numbers. I just computed them. So what? But imagine the performance of our eyes that are able to have this huge dynamic range of detection. It's insane if you think about it. It's over several orders of magnitude. For me, it's always mind-blowing to see these numbers. Here are some other examples of other magnitudes if you want to compute it, like the sun with minus 26, the full moon or Vega, so you can also compare it with these values. Just try it out, or go, for example, to Stellarium, click on some stars, get the apparent magnitude and convert it to this irradiance so that you get an understanding, a little bit better feeling what these numbers are all about. Now, the very last thing I would like to show you is something called the absolute magnitude, because the apparent magnitude is the magnitude we see from Earth. So very faint stars that are very close to us have maybe the same brightness as big, brighter stars that are far away, right? This kind of makes sense. But to have a metric to compare the brightness of the different stars, we have something called the absolute magnitude. And the absolute magnitude is the equation here where we have the apparent magnitude and also in our equation the distance in parsec. And yeah, so yeah, the one parsec is around 3.26 light years. Maybe I will do another compressed video about what is a parsec actually, because you hear it sometimes in Star Wars or so that are talking in parsec and something like that. But why parsec? Why not talking about light years? I think that we will do this in the next video. But if we just you put the values of Vega in this equation, we can compute, for example, here the absolute magnitude of Vega. And if we do the same thing for the other stars, we can compare the brightness of Vega with other stars, let's say. So we can determine, for example, is our sun compared to the other stars kind of big and bright or more average, right? So you have like a normalized reference frame where you put all the stars on the canvas and compare them, let's say, by the brightness, by the actual brightness, so to speak. Now for Vega, we have a magnitude of 0. It's around 7.7 parsec away. I took the values quite easily from Wikipedia, to be honest, where we have also the absolute magnitude of around 0.6. And let's see if we put the values in our equation, we compute it, and we get a value of 0.57 roundabout, which is pretty okay. I mean, I just took the rough values, so there's also some error I didn't consider, but it was just for the sake of showing you what this magnitude is all about, right? Well, that's basically for the coding part. I hope you learned something today. It is hopefully, it's not the longest code, but it's a very important concept, the concept of brightness in astronomy. To understand it, we will also talk sometimes with about other objects like asteroids and comets and also galaxies. So having at least a feeling of this brightness value is kind of important. So take stellarium, look for the different stars, go outside, check them out with the naked eye. You will see that a star of a magnitude of around 2 is twice as bright around, let's say, than the magnitude of 3 or so. And well, of course, our human perception, our eye has some kind of, let's say, logarithmic perception of brightness. As I said, we have also very high dynamic range, so it's not very linear, of course. The same, I think, applies also to the hearing, but yeah, I'm not a physician, so I'm not pretty sure about that. But again, I think these values are very stunning to also take this into perspective, how sensitive our eyes are. And now consider also that we observed objects in the universe not with a magnitude of 6 or 7 or 10, but even 18, 24, 25, 26. And if we take the watts per square meter and consider the potential energy of photons and so on, then we are talking about detecting objects where we only see, let's say, a photon per minute, which is insane, really insane. But also this would be something to compute. It's maybe not really astrophysics, but more like quantum physics, you know, to convert these values to a photon count. Let's do this maybe in the second video. So the next one will be maybe about parsec, to get you an understanding what a parsec is. And then we will talk about a little bit the irradiance a little bit more. And I think then we have like a good concept to understand what's going on. I hope you learned something today. Stay curious as always, and see you next time.